Um, and so the lab exam is going to be, the questions on the lab exam are going to be like the questions that you did in the labs. So just be sure you understand the thought process on the questions in the labs. No, I'll give you any formulas. And you won't have to use, yes. Yes, all the labs are on D2L. So yeah, you can print those or whatever to help you get ready. Yeah, I'll give you any formulas. There. So labs 1 and 3, it's pretty easy to imagine how I could write test questions based on those, right? If you remember, you know. But lab 2 is sort of a weird one because that was the one where we used the spreadsheet and everything. So I'm going to boil down lab 2 for you right now into half a page of the only things you need to get out of that lab. Okay? And I'm going to ask questions from this half-page list of things. Lab 2 for dummies. No offense. So first of all, you need to know the 3 things that I said affect, determine the effect of air resistance on an object's motion and in what direction they affect it. So increasing the object's mass, leads to a reduced effect of air resistance. Decreasing the surface area reduces the effect of air resistance on the motion. And then the last one is speed. Decreasing the speed reduces the effect of air resistance on the motion. And there's also the one that I talked about a little in lab that just the shape itself can affect it. But that's sort of a complicated relationship, so I'm not going to talk about that. What? The direction of, I don't remember. Oh, the direction. I mean this direction. I mean, if you want to reduce, like, if you're looking for the optimal thing that will not be affected by air resistance, it would have a large mass, small surface area, small speed. Okay, that's what I mean by direction. And then I said half a page. This is way less than half a page. The only other thing is dropping objects from 20 meters or less. Less than 20 meters. Air resistance had surprisingly little effect on fall times, Oh no, there's one more thing. One more thing. Like, if I could pick one thing for you to just never forget, to be like 80 and still be able to be like, if there weren't air resistance at all, any 2 things would fall the same. No. Without air resistance, any two objects would fall the same. Same fall times, same acceleration. So if you know all this stuff well from Lab 2, the only other questions that aren't based on this will be from Labs 1 and 3. And it, you know, anybody have any questions about labs right now? I know I didn't ask you to like prepare questions for that or anything, but how long the test will be? Well, you have the whole time, but I'll probably write it to take about an hour. That'll be my goal, you know, like I think most people be gone before the time's up, you know. But you can take the whole time if you want. Any other questions? It's going to be really just like what the questions you did in lab, except it'll be like instead of an elevator, it'll say canary or whatever. You know what I mean? Well, actually, even on the elevator problem, it said car halfway through or whatever. So it doesn't even matter. Yeah. Yes. In lab, yeah. In everybody's lab. So, and if you want to take it at a different one of the labs, you can just show up to one of the, you know, I have 5 different labs if you look on the syllabus, so go to whichever one works for you. And we'll just take it in that room, and it'll just be 5 different versions of basically the same questions, you know. Yeah. So there's no new lab next week, just taking the tests. Any other questions? Okay. So now let's go through the exam. So the first one, a rock is dropped from a bridge and it takes 1.4 seconds to hit the water. What's the height of the bridge? That's just the railing. That's not the whole bridge. And it takes 1.4 seconds. And we want to know how high the bridge is. So time equals 0 is when it's dropped. Time final is when it's water. Position equals 0 is the water. And the positive direction is up. Okay, do we know the amount of time it takes to hit the water? Do we know time final? Yeah, that's given. So time final is 1.4 seconds. Do we know the initial position? Do we want it? Yes, that's what we're asking for. Do we know the final position? Initial velocity? It's 0. Yes, we do know that. So anytime something's dropped, the velocity when it's dropped is the same as the velocity of what it's dropped from. Okay, so if it's dropped from a bridge, it's 0. So V initial is 0. V final, we don't know, but we don't care. And then acceleration, it's free fall, so that's negative 9.81 meters per second squared. And it looks like we can use this equation. P final is equal to P initial plus V initial time final plus 1/2 A time final squared. So 0 is equal to PI plus 0 minus 4.905. That's 1/2 times 9.81 meters per second squared times time final squared. And so PI is equal to, oh, and time final we know. I'll just put in 1.4 seconds squared. So PI is equal to, what's 4.905 times, what's 1.4 squared times 4.905? .867 meters. And then this one doesn't ask for anything special for the answer, so that's it. Any questions about that one? Okay, so the next one, the ball starts rolling up the incline at A, and its initial speed is 5.6 miles per hour. After 1.5 seconds, it reaches point B, and we want to know the acceleration and how far up the ramp it goes before it starts to come back down. So what's the highest point on the ramp? So the idea is that the ball rolls past B to some other point. Yeah, question? 9.6. Okay. .6. I don't remember what the answer is. Okay, so it's 4 feet between these 2 points, 5.6 miles per hour at the start. And it takes 1.5 seconds to get from A to B. There was not? That would be a lot harder. Okay, so first let's do the conversions. 4 feet, 3.281 feet is a meter. Can someone divide 4 by 3.281? 1.22 meters. And then 5.6 miles or hours. 1 mile is 1609.344 meters. 1 hour is 3,600 seconds. So can someone multiply those? 2.5? 2.24 meters per second. Yours is bad? It is 2.5. I fell for the extra significant figures. I was seduced by higher precision. That's a danger. 2.5, like 2.50? Wow. That's weird. Okay. Okay. So now we'll choose time equals 0, time final, position equals 0, and positive direction. Time equals 0 is when it passes A. Time final is when it passes B. Position equals 0 is A. Positive direction is, let's say, up the ramp. Um, 2.24 is 5 miles per hour, isn't it? Is that what you did? Yeah. I knew I recognized that number. Okay. So do we know time final? I think that's given. 1.5 seconds. Do we know initial position? Yep, that's 0. Do we know final position? That's 4 feet in the positive direction. So that was 1.22 meters. Do we know initial velocity? Yep, that's 2.5 meters per second. Final velocity, we don't know. And the first thing we want to find is the acceleration. So we can set it up as P final is equal to P initial plus V initial time final plus 1/2 A times time final squared. So 1.22 meters is equal to 0 plus 2.5 meters per second times 1.5 seconds plus 1/2 times, I'll do the T final squared, 1.5 seconds squared times A. 0.5 times 1.5. 3. And so what's 1.22 minus 3.75? Okay, so we have negative 2.53 meters, and then I'm dividing that by everything that's multiplied by A. So we have, that's going to be 2.25 seconds squared here. Seconds times seconds, and then the 2 is in the numerator. And so what's 2.53 times 2 divided by 2.25? It's like 2.25 is the answer. Negative 2.25. Okay, that makes sense, I guess. Okay, does it make sense that the answer is negative? Yeah, because the velocity is positive and it's going up the ramp, so it's slowing down. Then for part B, we want to find how high it goes up the ramp before it turns around. So we're going to have to make some new choices. We can still keep our time equals 0 when it crosses A. But our time final now has to be when it reaches the highest point. Position equals 0. I'll make that A. Positive direction up the ramp again. So time final, we don't know. P initial is 0. P final is what we're trying to find. V initial is still whatever that was before, 2.5. V final, what do we know about the velocity when it gets to the highest point? 0, yep. And then acceleration, we know that now, is negative 2.25 meters per second squared. So it looks like we can use the equation that says 2a times the quantity pf minus p initial is equal to v final squared minus v initial squared. So 2 times the quantity negative 2.25 meters per second squared times the quantity pf minus 0 is equal to 0 squared minus 2.5 meters per second squared. And so negative 4.50 meters per second squared times PF is equal to 6.25 meters squared per second squared, negative. And so PF is equal to negative 6.25 meters times meters, divided by seconds times seconds, divided by negative 4.50 meters, seconds times seconds in the numerator. And all the seconds cancel, one of the meters cancels. And what's 6.25 divided by 4.5? 1.49? Okay. So 1.5? 1.5? 1.39. Oh, okay. What? Okay. We'll call it 1.4 meters. And then it asks us to put it in scientific notation. So let's call it 1.40 meters. Put it in scientific notation in millimeters. Okay. So put this in millimeters. Well, we know that 1 millimeter is equal to 1 times 10 to the minus 3 meters. We know that because that's what milli means, so I just replaced milli with times 10 to the minus third. And so now 1.40 meters, and now I'll do it like a unit conversion. We have 1 times 10 to the minus 3 meters in the denominator, 1 millimeter in the numerator, and you get 1.40 times 10 to the positive 3 millimeters. Any questions about that one? Okay, I'm going to take a break for a second. Okay, so it's launched into the air. This is 5 feet. It hits the ground 3.5 seconds later. Is that what I said? Um, and we want to know what's the velocity at the instant it's launched. Time equals 0, let's make that when it's launched. Time final is when it hits the ground. Position equals 0 will be the ground. And the final, that's not what we're doing. This should be positive direction. Positive direction is up. And then list out what we know and want. Time final, we know, that's 3.5 seconds. PI we know, but I haven't done that conversion yet. 5 feet. 3.281 feet is 1 meter. So what do you get there? 1.52 meters. So P initial is 1.52 meters. Do we know P final? Yes. 0. Very good. P final is 0. Do we know the initial velocity? No, we want that. Final velocity? No. Don't. Yes. But that's a really easy mistake to make. So that's why. Remember that if we're talking about the flight of something, we can only do our calculations up until right before it hits the ground. And right before it hits the ground, it's still going down, you know? And it's such an easy mistake to make because when something hits the ground stops it. By the time the ground stops it, these equations aren't valid anymore. That's the thing. Okay. So we don't know, I should have said V initial. We don't know V final. Do we know the acceleration? Yes, free fall. So is there an equation that works with these? Yes, I think this should. P final is equal to P initial plus V initial times time final plus 1/2 A times time final squared. So 0 is equal to 1.52 meters plus 3.5 seconds times VI plus 1/2 times negative 9.81 meters per second squared times 3.5 seconds squared. So 0 is equal to 1.52 meters. What's 3.5 squared times 4.905? Okay, so minus 60.09 That'll be in meters, and then plus 3.5 seconds times VI, and then 60.09 minus 1.52 is 58.57. Yes. I always like yell numbers out, and then every once in a while they're right. But I don't remember what I said now because I got so excited. 58.57 meters divided by 3.5 seconds. And what's that? 15.7 meters per second. Does it make sense that that's positive? Yes, because it's moving up at the instant it's thrown or launched. And then we have to put this in some wacky thing. Millimeters per hour in scientific notation. So 1 millimeter is 1 times 10 to the minus third meters. So 16.7 meters divided by seconds is 1 times 10 to the minus third meters with 1 millimeter in the numerator. So that converts to millimeters, and then we have to do seconds to hours. So 1 hour is 3,600 seconds. And what's 16.7 times 3,600 times 10 to the third? What is it? 6.0 times 10 to the 7th millimeters per hour. And then the last one is one of those plot a position versus time graph. So a ball rolls along the floor, hits the wall a meter away after half a second, then bounces off and returns to the starting point after half a second. And time equals 0 is when it starts to roll. So okay, so that's what happens. It takes half a second for the ball to, so it goes from A to B in half a second, and then it goes from B back to A in half a second. So if I put this on a number line, the distance between those is 1 meter. The motion starts here, goes to here, and then back here. Okay, so for part A, we're going to, for both of them, we're going to let time equals 0 correspond to when the ball starts rolling. So this instant is going to be 0 seconds. And so half a second after 0, this is going to be labeled 0.5 seconds. And another half second, this is going to be 1 second. And now for part A, 0 is at the ball's starting point and positive is toward the wall. So this is 0 position. Positive is this way. And so if you start at 0 and go 1 meter in the positive direction, what's the label for B? Yep, positive 1. And now we can just read these as like coordinates. At this first instant, we're at 0 time 0 position. At the second instant, we're at 0.5 time 1 position. And then at the third time, we're at 1 time and back to 0 position. So the points are 0, 0. This is 0.5 seconds, 1 second. 0.5, 1, and then 1, 0. Something like that, or you can round it off. Any questions about that one? And then the second one, now the 0 position is at the starting point and the positive direction's away from the wall. So the only thing that changes, so I'm going to take this. So this is still the 0 position, but now the positive direction is this way. And so that's going to change this position label. If you go 1 meter in the negative direction from 0, where are you? Yep, so this label is -1 meter. And so the coordinates are 0, 0, 5, -1, and then 1, 0. And so now this is position, this is 0 position, and this is -1 position. This is 0.5 and 1 for time. And we have that, that, and that. It just sort of depends what it sort of goes case by case, so I can't really say that for sure. That can be the case. It just sort of depends how, like, you know, if it's like how significant a thing it looks like it is to me, you know what I mean? Yes. I think I would probably not take off any points for that. I don't know, did you write all over like, oh my God, what's an hour? Like, or anything like that? Because that would give me a clue that maybe it was significant, but otherwise I think I would just assume you. What does an hour even mean? That probably wouldn't take off any points for that. I can't imagine taking off. Any other questions? Yep. Well, all I do at the end of the semester, I might curve it, the final grade. I don't do it test by test. I don't give grades for each test, you know what I mean? It just all adds up into this formula. So not really for the test, but like if at the end I feel like there's too few A's, or the grades are skewed from where they should be because maybe some tests were harder than I meant them to be or whatever, then yeah, I'll curve it. Any other questions? Yeah. Sometime before, but I'm not sure how much before. You know what I mean? Because that's the only place I keep track of my grades is on D2L. So as soon as I do it, it'll be up there. Yes. There were 4 questions, so 24. I usually just do 6 per question, and then I sort of, instead of doing it like 1 point off and 2 points off, I sort of, on each question, just sort of say like, how well did it look like this was understood, and score out a 6. Any other questions? Don't you guys sort of just want to stop? I mean, for real, don't you? I do. Okay, let's do that.
Problems that you did.
Yeah.
I wasn't sure where you got the 2 out of nowhere.
Okay. Let me just save this and then we'll look at it. Okay. Which one was it?
The second one, I think. Keep going, like number 2, I think. Okay, yeah, right. Yeah. So I wasn't sure where you got the 2.
Oh, that's the half from this equation.
Wait, what did you have like divided?
Oh, that kind of thing. That is the kind of math thing that I think I probably wouldn't take off any points for. Yeah. I mean, I'll have to see the problem, but like if you just forget a 2 in a formula or whatever, yeah, like I wouldn't. Yeah. I don't think so. No. Yeah. Okay.
Right, I might be losing my mind, but on problem 2, I swear, like there was no, on my paper, there was no like 4.
Okay. Well, if
do you have like the test?
I don't. Okay. Well, we'll talk about it after. Okay. I mean, if I somehow gave you the wrong test, for sure. I mean,
yeah.
We'll deal with that.
I was creating that problem. I was like, wait, what's the A and B like?
Well, yeah.
So I took the 5.6 miles.
Okay. Yeah. That sucks. So I mean, it sounds like probably you just didn't see it, Yeah. But I mean, I suppose it is possible that somehow you got a test that was like an old document or something. I'll have to think about that a little, but let's talk about it after I grade it. Yeah. Okay. Yeah. Mm-hmm. Yeah. Oh. Okay, that's no problem. Yeah. Yes, for sure.
That's just an extra step.
Right, it does. Yeah, that's fine. That's perfect.
For the dropping the ball.
Yeah.
Okay, so the P, F, and P, right?
Well, you can do it either way. Well, yeah, I mean, if you think of your 0 position as being at the bridge, then you're trying to find P final, and it's going to be like a negative number. Yeah. Uh-huh. Okay. It sounds like that might be okay. It'll sort of depend on how it goes. Either way, you know, it won't be like a ton of points off. But yeah, that's a tough way to think about it, but that is sort of true. But I mean, that's good. That's a good start. Bye. Have a nice weekend.